Good afternoon, everyone.
Good afternoon, sir.
So today is lecture number 10 of this advanced concept in steel technology, and the topic is precipitation strengthening. So we have discussed a lot about strengthening mechanism, which is by dislocations, dislocation interaction, dislocation point defect interactions, dislocation and grain boundary interactions. Already we have discussed those things, and also we have seen something about transformation strengthening, which is due to formation of some non-equilibrium products like martensite and benites. But today the topic is basically a very interesting topic because precipitation strengthening is very important for certain applications where temperature is very high, but the temperature should not be very high because those precipitates again grow at a high temperature and the strengthening loses sometimes. And the things maybe happen like this: the precipitate may get soluble in the matrix phase itself. So if there will be no precipitate, there will be no strengthening again. So up to a certain limit or up to a certain temperature range, we are using this precipitation strengthening materials. Basically, the major application area is like aircrafts, making aeroplanes, aircrafts, uh, ship ship buildings, some military applications. These precipitation strengthening materials are used. It may be, let me show you. It may be certain steels. It may be some aluminum copper alloys in brush and super alloys also. We have precipitation strengthening. So now everybody understood now. Precipitate, you understand. Precipitate is nothing but a secondary phase, which will come out from the matrix during the aging stage, right? We'll see that again. I think you remember that. Again, I will discuss that, how the precipitates come out from a matrix. So you understand we have a matrix phase and we have a secondary phase. The secondary phase are like precipitate particles. So due to interaction of dislocation with the precipitate particle, the dislocation motion will get hindered. The dislocation motion will get restricted. Hmm. That means you can say like that the precipitate is pinning the dislocations. The dislocation is freely moving, and the moment the dislocation is coming in contact with the precipitate is pinning the dislocation. It is not allowing the dislocation to move easily in the material or in the matrix or in the slip planes, right? So that leads to the precipitation strengthening in the materials. So a precipitate and dislocation interaction will be there. So so how the strengthening in precipitation strengthening depends upon basically these four things. One is precipitate size and shape, precipitate volume fractions. Precipitate size, you understand, it is smaller or bigger. Shape means it is which kind of shape it is, spherical or something else. And precipitate volume fractions means how many number of precipitates are there in the matrix, more or less. And otherwise, the nature of interface between precipitate and matrix. What kind of interface is existing between the precipitate and the matrix? It is basically a coherent interface or incoherent interface, like that. Those things we'll discuss in coming slides. And crystal structure of the precipitate, that is basically again related to the interface, crystal structure, whether the crystal structure of precipitate and interface, sorry, crystal structure of the precipitate or matrix are same or they are different basically. So look at this image. This is a very good image. You can see this is a coherent precipitate, but this coherent precipitate is having this yellow portion is a precipitate. This precipitate, you can see there is some bending of the these. Actually, these lines are nothing but the, suppose you understand this part. This darker part is your matrix, and this yellow part is a precipitate in the matrix. Fine, it's a particle kind of thing, and these are actually lattice planes. Hmm. These lines are actually lattice planes or atomic planes, right? You can see there is a bending of the lattice plane inside the precipitate, or across the interface of the precipitate and the matrix. There is a bending of this lattice plane is there, right? So you can just look at this image. Hmm. Here the size of the precipitate is very big. That means suppose initially the precipitate size is this much and it is growing and becoming bigger and bigger. So the consequence is what? Some dislocation will get introduced here. You can see the dislocation are getting introduced due to increasing the size of the precipitate. Dislocation is getting introduced, and you can see some more bending of this lattice plane is there comparison to this one. Right? So here I have written a very good point here, which I will explain quickly. Coherent precipitate low activation energy, low activation free energy. Sorry, here we should write uh, not activation energy, no, low interfacial energy. Sure. Yes, coherent precipitate means we have a low interfacial energy. Hmm. Interfacial energy means the energy of the interface. Interface means precipitate in one phase, matrix is another phase. So in between the part is called interface. So coherent precipitate have low interfacial energy. That is why we have a low activation free energy. That is why easy to nucleate. So that means coherent precipitate is easy to nucleate in the matrix phase due to this low interfacial energy. And incoherent precipitate, here you can see it has high interfacial energy. Interfacial. It has high interfacial energy. And since it has high interfacial energy, so it has high value of activation free energy, due to which it is very difficult to nucleate. So this is the thing. We'll explain that. I will explain that soon. Just look at this. So before moving into the precipitation strengthening, we should know how a precipitate forms in a materials. So that means, okay, let me ask you questions. Do you, can you people tell me, uh, if we have a pure metal, precipitate will form, or if we have an alloy, then precipitate will form?
For alloy precipitate will
Obviously, for an alloy, very good, Vijay. For an alloy, because precipitate, you understand, it is a mixture of two phase basically. Basically, precipitate contains mixture of two phases, or it is a mix. It is a mixture basically, or you can say it is containing two metals or two elements, right? Like that. Or two elements, two metals may be there, or two elements may be there. Maybe a metal and non-metal will be there, like carbides, nitrides, a metal and non-metal kind of thing. So, how to get precipitation in an alloy? So, what is the thing? Super saturated solid solution by taking the sample to a single phase region. So, this is the first stage. That means we take the alloy to a single phase region first. So, when we take the alloy to a single phase region, we have a super saturated solid solution. So, which I have written over here, region in phase diagram. So, in the phase diagram, you have to go to a alpha region. Alpha region means it is a single phase region. Second, what we have to do, we have to rapidly cool the sample. That means we are doing quenching actually. From this region, we have to quench the sample where to two phase region, and have to wait for the precipitation to occur. So two phase region means alpha plus beta
Yes, sir.
region. Right. Sorry, Mansik, are you saying something?
Can you enlarge the slide?
Acha, enlarge. Okay. Now it is okay. It is visible now.
Yes.
Yes, very good. So, how to get precipitation in an alloy? The first stage is the you have to form a super saturated solid solution. How? By taking the alloy to a single phase region, which is the alpha. I'll show you the plot. I'll show you the phase diagram of certain alloys. After reaching to the alpha region, then you have to suddenly quench it, suddenly rapidly cooling of the sample. Where? To two phase region, and you have to wait. After taking the sample to the two phase region, you have to wait so that precipitation will start. So two phase region means alpha plus beta. So here precipitate is your beta phase, which is getting precipitate in the alpha matrix. You understand? Precipitate is the beta, which is precipitating in the alpha matrix. So stages are written over. Solutionizing. Solutionizing is the this stage. Then quenching. This is the rapid cooling stage. And finally edging. Edging means after reaching to two phase region, you have to do edging. Means you have to wait for the precipitation to occur. Right. So here I have written during precipitation, first thing is the nucleation. That means a nucleation will start. A precipitate will start forming. That means it is nucleating first. Then it will grow again. So which happens? The physical meaning of nucleation means what? Creation of a new surface or new interface between the matrix and the particle. That means between alpha and beta. Upon going from the single phase region alpha to two phase region alpha plus beta, there is a reduction in the free energy occurs. So change in the free energy is basically negative here. You can see a defect is created around the particle. Ways the nucleation occurs. So okay, fine. There is a way how nucleation occurs that is called heterophase fluctuations. There is a fluctuations occur in the matrix and in the precipitate. So particle forms and dissolve again, and when the particle is bigger than the critical size, then it grows, and finally precipitate will come out. That means some fluctuation is successful and some others are not successful. Right. So now this is a very good image. You can see this is an aluminum copper alloy phase diagram. This is not the whole phase diagram. This is the important part of the phase diagram of aluminum copper, and this is the important phase diagram part of the copper and zinc system. Brass. So you can see what is happening here. Just look at this one. So this is the liquid phase region. This is the two phase region alpha plus liquid, and this is the single phase region alpha, and this is the two phase region alpha plus beta. Right. So what we have to do precipitation in aluminum copper alloy? First, you have to heat the alloy to this single phase region alpha region. Right. The moment you take the alloy to this phase region, what will happen? A super saturated solid solution will form. Everything will be there in the solution now. Then you have to do quenching or rapid cooling. Now I am doing rapid cooling or quenching to this two phase region, this phase now. Here, for example, after reaching to this phase, now I have to wait for some times. The moment I can wait, I will get precipitates. I will get precipitate of beta in alpha matrix. I think you people have understood now. This is the temperature axis and this is the concentration axis. Fine. Again, this is temperature axis and concentration axis. So here, what is happening? You can see I have to heat the alloy to this phase alpha because this single phase region, everything will be there in the solution. Again, you have to quench it suddenly to this two phase region alpha plus beta. After reaching to this phase region, you have to wait for some time. Now precipitate will come out. Beta will get precipitate in the alpha matrix and will get precipitates. Okay, now this is a okay. Can you people remember this this image? Also, we have encountered this image while we are discussing about the solidification part in the advanced thermodynamics and kinetics. Can you remember what is this plot is saying? This is the free energy axis. This is the radius r. How many of you have remember? Let me see. How many of you have remember this plot? Free energy versus radius r of a particle. Yes, Vijay.
Sir, the atom needs to overcome an energy to a nucleus.
Atom want to overcome or atom?
Sir. So that.
Directly we get pure copper. Okay, we don't means in the conventional process.
Nuclei.
Yeah, okay, a nuclei, yes.
Nuclei, they have to overcome that.
A nuclei?
An energy barrier.
Yes, very good.
For nucleation, we need to overcome that energy barrier. So
What is the advantage of iron oxidation?
that.
Iron oxidation is
Okay, what is the relationship between R and this free energy? Radius of R and free energy.
It will also prevent the heat loss to the surrounding as well as it prevents the movement of copper in the slab phase. Okay, so we recover large amount of copper.
You can see with increasing in the radius of the particle, suppose a precipitate want to form in a matrix, so it will nucleate, but when it will nucleate, it has a particular size. So you can see initially when the size is smaller and the size is slowly increasing, you can see the activation free energy is more and more and more. But after sometimes when it reaches at this point, that is R star, that is called critical size of the nucleus or embryo, you can see after that the free energy is decreasing again. That means the growth will be possible. If the size is this much, or if the size is this much, this much, this much, again it will get soluble in the matrix. But if the size is this much, that means size of the particle is greater than R star, then it will grow again because free energy is decreasing. But from if the size is this much, this much, this much, the free energy is increasing, you can see, right? So you can see this change in free energy when a precipitate particle is there. So this is the equation we have: volume free energy and surface free energy here, because we are creating a new surface free energy, and this gamma is the interfacial energy per unit area, and del GB is the volume free energy. But what is this part? We have another part here. What is this part? This part is actually strain energy, because when a precipitate is forming in a matrix, some strain will be around the particles. So that's why we have to subtract this one from del GV, volume free energy. So that is psi, you can say. But forget all this. But the important part is this one. Look at this one. G star is proportional to gamma to the power q, but divided by del GB minus psi to the power square. So from this equation, can anybody get any conclusion from this? So activation free energy during a nucleation process or during a precipitation process is depending upon how? Can you tell me? We're looking at this equation. Everything is here. Look at this diagram and look at this equation. It is clearly showing activation free energy is directly proportional to the interfacial energy and to the power cube. That means more is the interfacial energy, more will be the activation free energy, right? More will be the interfacial energy, more will be the what? Activation free energy. So what will happen if activation free energy will be more? Nucleation will be easy or difficult?
Difficult.
Obviously difficult. Very good. But here it is to the power square, but it is to the power cube. So this is most important. As I told, when a particle, a nuclei will form, when a nucleation will be there, an interface will be created. And the interface is here, interfacial energy here. Right? If the interfacial energy will be more, G star will be more. If the G star will be more, nucleation will be difficult or precipitate will not form easily. Right? Okay, fine. Here I have written already. If precipitate is coherent with the matrix, it means interfacial energy is small. You have to remember this one. When a coherent precipitate is forming, the interfacial energy is less. Then it is easy to nucleate. But if the precipitate have lot of structure in it, like dislocation structure at the interface, that is incoherent, and the interfacial energy will be more, then the precipitate will be difficult to nucleate. So coherent precipitates are easy to nucleate, but incoherent precipitates are difficult to nucleate. Coherent precipitates are easy to nucleate because they have low interfacial energy, right? So activation energy barrier, activation free energy is less. But if for an incoherent precipitate, they have lot of dislocation at the interface. You can see this is a incoherency. You can see lot of dislocation. This is a dislocation. This is a dislocation. This is a dislocation. This is a dislocation. So lot of dislocation are present at the interface. So interfacial energy is more here. But here there is no dislocations here. So interfacial energy is less. But there is certain strain. But here the strain is more here, right? So it is written. Same thing is written over here, right? Just look at this one. Basically, in complete coherent precipitate, the crystal structure and the lattice parameter of the precipitate are the same. The precipitate and matrix have same crystal structure. If it is FCC, this is FCC. and the lattice parameter is also same. If lattice parameter is something, lattice parameter is same here. So basically that is called complete coherent precipitate, right? Sometimes what happens, strain but coherent precipitate. So this is the situation. We have certain strain. So strain will be there because lattice parameter is not matching. Crystal structure may be same. Precipitate crystal structure and matrix crystal structure are same, but the lattice parameter is not matching. So there will be a bending of the lattice plane will be there. So some strain will be there. But suppose this precipitate is growing more and more and more. So what may be the situation? The precipitate will become more and more. So there will be more bending of this lattice plane. So more bending of the lattice plane will be there. Suppose precipitate will go more bigger and more bigger. So more will the bending. A time will come, there will be a lot of strain in the material will be there. So what happens? There will be no further bending. There will be introduction of dislocations here. Right? When the dislocation introduction will be there, it become incoherent precipitate. So basically, incoherent precipitate do not have same type of crystal structure maybe. The lattice parameter is not also same, and basically incoherent precipitate are bigger in size, which it is showing.
Higher amount of copper metal will produce. Okay, if I supply less amount of oxygen means copper met level.
I think you people have understood this one.
Then here
And
is present in this dipole.
Dislocation precipitation interaction. So how strengthening will happen? Strengthening will happen when dislocation is interacting with the precipitate. So there are two ways by which the dislocation is interacting with the precipitate. The first way I can say is bowing of the dislocations around the precipitate or shearing of the precipitate by the dislocation. This shearing of the precipitate by dislocation may be called cutting, or I can say dislocation will cut the precipitate. So here how this is happening. Now if somebody will ask what is the condition, condition when the dislocation will bow or dislocation will cut the precipitate. This may be the questions. What is the favorable condition when the dislocation moving and cutting the precipitate into two halves, or what is the situation when the dislocation is moving and bowing around the precipitate? You can consider a precipitate as a particle, obviously. So what? Answer is if precipitate is coherent then shearing or cutting will take place. Similarly, if precipitate is incoherent, bowing will take place. Or I can say if particles are weak, then it will cut.
Now next one, this is meteorology process.
Particle are weak, then it will be cut. If particle are strong enough, bowing will occur. I don't have the images right now. I'll show you the images tomorrow. Definitely.
Electroslack-leaning furnace, converting furnace. But
Again, I can write here.
वक्र process कौन रहता है? अपन तीनटे जाको furnace गुप्ते line में रहते हैं. Constant state of motion.
Coherent
But
precipitate.
गुप्ते furnace.
Coherent small precipitate. Precipitate is coherent and small. Small precipitate, you understand, there will be less bending or there will be no bending. You can understand bending of the lattice plane across the interface. And precipitate is small. Coherent and small precipitate. Dislocation interaction. Interaction.
So in this furnace, we directly produce blister copper rather than copper.
So situation is what? Situation. So I can say here when the precipitate are small and coherent. Okay, fine. Can you people tell me if the precipitate size is small, the spacing between the precipitate will be if the precipitate size will be smaller, the gap between the precipitate will be large or more? You suppose you take two samples. In one sample you have bigger precipitate. In another sample you have smaller precipitate, but the volume fraction is same. So the gap will be more where, the gap will be less where.
So gap will be less for small.
Very good. Very good. Condition applied is volume fractions would be same. Okay, very good. So here when the precipitate are smaller and coherent, the spacing between the precipitate particle is smaller, due to which Boeing will not take place. It's required more energy for that. So what happens? The dislocation will cut will shear the particle. Now the question is consequence. Consequence of shearing. Shearing here means cutting, same thing. Consequence of shearing of particle. Particle here means precipitate. So what may be the consequence? New interface will be created. Yes or no? New interface will be created because single particle is cutting into two halves. That means new surface is created or new interface is created between the particles. Right? Between the particles and matrix. Right? Due to this, interfacial area increases. Area increases. Due to which interfacial area increases, which leads to what? So increasing the energy, interfacial energy. Energy, right? Which keeps rise to strengthening.
That is very copper metal is very less and impurity amount is much more. Up to this much is clear?
Strengthening.
Hello?
So what happened if a new dislocation,
That reality will take place and in the
if a new dislocation will
reduce the copper. So today is this much.
if a new dislocation
I will say
moving
slide to
on same slip plane
your copy along with book. Okay, so that you can get for this one.
find its difficulty in cutting it. Right. So conclusion, you understand. So first, what happens when the precipitate is very small and coherent, dislocation is moving and cutting the particle, and dislocation is going away easily. But once the dislocation is cutting the particles, new surface area is created because single particle is becoming now two particles, two halves. You can understand. Single spherical particle is becoming now two half. Right. So new surface area is created, new surface area or new interfacial area is created between the matrix and the particles. So interfacial energy is increasing. If the interfacial energy will increase, then when the next dislocation will come, it cannot cut the particles. So that is the strengthening mechanism here for a small and coherent particles. Similarly, if we have a larger and incoherent precipitate interaction with dislocation. Dislocation interaction. How they will interact. So here bowing occurs instead of shearing, right? So they are actually four stages of interaction. Four stages of interaction between particle and dislocation. And this mechanism is similar to that of your Franklin source kind of thing. So stage one, you understand. Suppose I'm writing stage one. So what happened in stage one? Dislocation and precipitate are near to one another. Dislocation is close to precipitate particle otherwise. Stage two will be what? Dislocation bowing between the precipitates. Dislocation bowing between the precipitate, because it is dislocation close to the particles. Many precipitate will be there. Suppose you consider 2 to 3 precipitate are there with a gap in a straight line. So dislocation line is moving from left to right. So first they will come closer to the particles, then dislocation bowing between the precipitate. In between the precipitate, try to bow. Stage 3 is what? With more shear stress. More shear stress leads to more bowing. More bowing. Leads to more bowing of dislocation around the particle. The particles, right? Finally, the stage 4. What is happening in the stage 4? Do anybody remember this one from BTech class? What happens at the end? Hmm?
A circular loop of dislocation will form.
Very good, very good. Circular loop of dislocation will form. So what happens due to opposite Berger vector or sign of dislocation? 2 will get annulate. Two will get annulate. Two will get annulate each other and results in leaving a loop around the precipitate. Right? And dislocation will cross away. Cross away from precipitate. From particle, precipitate, whatever you want, right? You can write. And this part is bowing up the dislocation around the precipitate is similar to that of Franklin sources, I have told. So consequence, what is the consequence now? Consequence of loop formation. What happens when a new dislocation will come and it will look that there are loops around the precipitates. So what will happen? The gap between the, so what will happen? The gap or the spacing. So spacing will increase or decrease if the loop will be there around the precipitate. Who can answer?
Spacing will decrease, sir.
Obviously, because there is a dislocation loop, spacing between the particle is decreased due to formation of this kind of decreases due to this formation of this kind of loop. So dislocation find it's difficult in bowing, which leads to the strengthening effect. Right? This is the situation here. So initially distance between the bigger incoherent precipitate has reduced from particular length to a new length due to the formation of dislocation loop. That means when one dislocation passes away through this precipitate, it leaves loop of dislocation around the each particles. When the next dislocation comes from it, less distance will be there. So it finds very difficulty to bow down through and strengthening will increase, definitely. So okay, I will end the topic here. I'll show you the pictures in the coming class. Okay, you people can leave.